start having those spurious resonances, and you can't use that data. It's garbage. So, you know, you see these specifications where people say, oh yeah, we can measure up to 1,000 hertz, but the sensor is giving bad data once it gets above 350 hertz, and it's just not usable. Next chart. So, you know, we did the testing at the site in, you know, at our, I guess, in our lab, and then we said, okay, we really need to go out to a test facility that's controlled also, because originally we were doing all these tests at other people's sites, and, you know, we'd go in and we'd produce the data, they'd look at the data, but we didn't get their data. All they did was get ours, and they compared it to what they were doing. So we said, we should do this ourselves. So we said, like, where should we do it? So we went out to this Divine test site, and this is a industry standard site. It's right outside San Antonio. It's been used for years. They have all kinds of data, you know, stable data. They have calibrated by all kinds of different tests they've done over the years. And basically what they say is it allows people to come out and see if their tool actually works. And so that's what we did. So, you know, they had several wells there, typically on, you know, about 3,000 feet. And this shows kind of our setup. You know, our truck there, there's the well, and the stuff being lowered into the well. Next chart. Now, I'm going to try to explain this without getting into a lot of detail, but here's an example of data that was taken at that test site with our geophone. And, you know, here I'm talking about a vertical one, because when we put the sensors in the well together, there's the X, Y, and a Z. There's one going vertical, one going this way, and one going this way. So it gets the directionality of the incoming waves. So what this chart shows is, this is time over here in milliseconds, and this is shot point. So we put the stuff in a well. We're down, let's see here, 550 feet. And then we have this noise source. It's called an accelerated weight drop. And we do shot points. And this is typically, they call a walk-away test in the oil industry, where you get close to the well, you go boom. You go another 25 feet, you go boom. And you do this, and you step away from the well, and you do this, and you look at the data. And so what happens is so when you hit the ground at, say, every 25 feet, it takes a while for that sound energy, once you go hit, to get to the sensor. And so this point here is, there's that time from zeros when you pound the ground, and 50 or 75 milliseconds later is when the sound hits the sensor. That point there where you first pick it up is called the first break. This is very important for microseismic monitoring, because basically when you're measuring events such as a microseismic event, the first break is actually tells you, you know, the timing of when that event happened. If you have multiple arrays in there, then they match all those times, and they could figure out by triangulation where the event occurred. It's kind of like, I don't know if any of you guys maybe sail or do something like that. Before they had the GPS and all this, you're sailing around, you're trying to figure out where you are. You take a fix on 3 different things, right? And then when you draw it on the chart, they all intersect. You go, okay, that's where I'm at, you know, in the channel. It's the same thing with microseismic, right? I mean, you're looking at these events, fracture events that occur from a bunch of different locations, and where they all come together is where you say, okay, that's where the event happens. And how they determine that is based on time of the first break. So that's very important to make a point. But the other thing I want to point out, and you can see that as you step away from the well in 25-foot segments, that first break is occurring later and later, which of course makes sense, right? You're moving further away, it takes a little more time for the signal to get to the sensor, so the first break is a little bit, time-wise, a little bit longer distance. The other point I try to make here is that, you know, you look at these lines before the event happens, and look how flat they are. That means it's basically low noise. There's no noise on the system, and the noise occurs when you hit the weight drop, and that's very, very important. So I'll show differences later. But what we wanted to do was compare our vertical geophone to the oil, conventional vertical geophone, and then a horizontal geophone to an oil conventional geophone. We did do the comparison to the horizontal, but the data for the vertical was just so bad that we got out of that conventional geophone. It was pointless to even put it on the screen, and we were struggling with it. We go like, you know what? Either that geophone, it was so bad that something possibly was wrong with it, or it's worse than we think they are. So we didn't compare the vertical, but we did compare the horizontal. So the next slide shows a horizontal geophone in the same well, and same thing. You can see these are the the first breaks that are occurring, and as you step away, they take a little bit longer, and then here's all the data. And then what I'm going to want to do is the next chart compares our data to the conventional geophone. And what I'd like to do, Alexander, is like show that, but then if you could switch back and forth. So I'm going to show some things first, and if you switch back and forth so you can kind of see the difference. But notice, like, there's no clean first break. And if you're going to monitor microseismic, that's important, because if you don't get a first break, you don't know the timing and tie things together for where the fracking event occurred. You do see some things, because we know what the first break is from our stuff, but you're seeing some of it here, but it's hard to really pick out. And out here you see nothing, and you don't start seeing like some of the slower speed waves. Typically, like shear waves are slower, and I'll bore you with a lot of seismic information, but shear waves are slower, so they come later, and a lot of them sometimes are higher amplitude, so they didn't pick up anything till some of these shear waves started coming through. And this is the best conventional sensor out there. So flip back and forth just several times if you could do that between those two data. I'm saying go to the horizontal and the and that one. Okay, can you flip back and forth so people just and so as she does that, notice the spacing of these events between the two. And if you flip back between hours, in reality, what that tells you is we get much more high frequency data. And you can see that, look at the spacing of all these events versus the other one. It's just further apart. And that really comes down to resolution. It's kind of like, you have a TV with better resolution. They see things better. If you get higher frequency information, you see things better. And it's obvious here looking at it that, frequency-wise, our frequency content is much higher. So this is really, really good data showing clearly, how much better our system performs in a controlled environment in a test well. Next slide. Okay, so all that being said, so what are we doing here? So our point is that we know, and we've been talking with our clients, and they're telling us, you know what, we don't want one of anything or 10 of anything. We need hundreds of thousands of these systems. How are you going to be able to do that, right? And so we've had the leaders for these companies come out and check us out, and we're showing them what we're doing. And, here's some of the things. We need to staff up. A little over a year ago, we were about maybe 7 or 8 people, and now we're pushing 50. So we're staffing up. We hired a recruiter. I don't know if you saw Kimberly in the back, corporate recruiter and HR manager to help us do that. She's been doing. We're looking at acquisitions. There are several that we're looking at that have a manufacturing capability that is being underutilized, but it's the expertise we want and the capability we want, but they're applying it for an industry that, it's being underutilized. So we're looking at these and possibly picking that up. We have a bunch of different contract manufacturers looking at to kind of outsource some of the stuff that we don't have to do in-house. And then the other part is we make our stuff like, rather than trying to develop a processing and recording system, we go, you know what, we'll put ours in a format so we can hook up to anybody's processing and recording system, so we don't have to do that part. So that's another important thing, which people like. They tell us what format they need. We tell them what we're doing, and we say you don't have to, we don't have to do it. You don't have to redesign your recording and processing system. will be compatible. Next chart. You know, then we have all these standards we have to comply with. You know, legally, you can't ship stuff out the door if you don't meet these things. So we're going through and make sure everything we have meets these things. So, you know, FCC, CE, which is the Europe stuff, UL, all these different types of certifications. We're getting all these, so when we start shipping out the systems en masse, it meets all those regulations. Next one. You know, example being, and you'll see this later today, is you know, we have this set up, so we're trying to crank these systems, get them out the door, but you know, certified all the FCC, the CE, the IC, you know, all these different certifying bodies. We're taking out there, getting our equipment certified at these, so have no problem shipping them in the U.S. or around the world. You know, somebody asked me earlier, you know, what else you're doing? It says we're really increasing the automation of how we make these things, and we list some of the things here. You know, stripping. You say, okay, what does that mean? So you have optical fiber. If you know, think in terms of wire. You get copper wire, it has some insulation on it, and before you solder to something, you have to take the insulation off in order to solder it. Well, fiber's, you know, not that much different. You have to strip the jacket off of it before you can splice it together, which is fuse the glass together. And, you know, typically that's really easy to do with standard fibers that you use that are low temperature. But an example being, several of our systems, our clients are asking for a high temperature, and you have to use a special type of coating on the fiber. And the standard way of getting that coating off the fiber is heating up sulfuric acid to almost boiling and dipping the fiber into that fluid and letting it dissolve, and it takes like 10 minutes. And plus you have this boiling, you know, sulfuric acid, which is dangerous. So, you know, we didn't want to go there. So, you know, we talked to companies and they built us these systems where we mechanically strip off this coating, where we stick it in the machine, and in the order of seconds, this coating's off, no chemicals, and then we can splice. That's an example. We have several of those we brought in-house, like 3 of those. You know, splicing, we've got the best splicers and all the automated splicing equipment that, you know, that's on the market. Recoating, once you splice, you need to recoat it with something, and so we've got automated recoders in-house, so that's all done automatically. One of the things we'll show you today is that, you know, when we were initially building these systems, you know, we could wind them manually. We had 2 stations, and we could produce on the order of, you know, maybe 10 geophones per shift, right, or something that per station. So we could say maybe do 20 a day, and you know, that's okay for low volume stuff. But you know, it was all done manually. The person winding it manually. So we contracted a company. It was the same company we used to develop the automated winders at when I was at Lytton, Northrop Grumman. They designed custom winder for us, and now we can produce, you know, with this custom winder, automated, you know, 10 at a time, and produce on your 250 to 300 sensors per shift, and that's what we wanted. We're going to order another one. So the first one came in maybe a week ago, and we're going to be ordering a couple more as needed to handle our volume. You know, calibration, all that is standard, and you know, when you're testing stuff, you got to make sure all your equipment's calibrated. And you'll see, and if you've been there before in our facility now, we're in a 22,000 square foot facility. It's packed.